Alright, welcome back again to our video lectures, and we'll do our last problem for the conservation of mass, or the continuity equation. Okay, so the problem says water discharges over a spillway as shown. Okay, so this is a hydraulic structure common to canals and open channels situations. Okay, so water discharges over a spillway. The depth behind the spillway is 24 feet. All right, so that's in English units. So 24 feet spillway, and the downstream channel are both. It says here, spillway and the downstream channel are both 50 feet wide. Okay, so that's 50 feet refers to the width. That's the orthogonal length. Okay, that's the if this is our plane, then that's gonna be our the orthogonal length. That's 50 feet. 50 feet here. That's also 50 feet downstream channel. Okay, the depth at the toe of the spillway is 0.41 feet. Okay, so we have here 0.41 feet. Assuming that the surface velocity behind the spillway is very small, such that the velocity head can be neglected, and ignoring friction losses on the spillway face, what is the discharge over the spillway? Okay, so we have our head right here, and of course, since it's a spillway, and the figure also shows us that the depth is greater than the spillway, and therefore we'll have something like this, a discharge going to the downstream. It says here, what is the discharge over the spillway? So what is the discharge somewhere here? Right, so for the solution, I guess it would be best expressed in terms of 3D drawings. Okay, so converting the given illustration into 3D to 3D. And by the way, this problem is taken from the textbook of Cruz et al., and that's example 5.7. And this is the textbook, right? Introduction to Hydraulics. Okay, so now let's draw. Now, let's say this is our spillway, and we have a 50 feet, something like this. And if this is the XY view, we'll have a view like this, XY, and then this will be our Z-axis. Okay, and the depth here, we have a higher depth as compared to the spillway, and here we have depth of, that's right, this is 24 feet, and then this one is 0.41 feet, and here this is our 50 feet. Now you would notice that we will have something like a rectangular section right here. That's going to be our area. So if we have the velocity, or it will just be the same as this, I guess it will just be the same as this cross-sectional area until right here, right? So it will just be the same. I mean, ideally that would be the same. Okay, so we have 0.41, so of course this will be 0.41, this will be 0.41. Okay, so now let's also draw another one right here, so that we can also we can put some notations. Okay, so we have 24 feet, and this is 0.41 feet, and it says here that the surface velocity behind the spillway is very small, such that the velocity head can be neglected, ignoring friction losses on the spillway face. So that means that we have to utilize the Bernoulli's equation. Okay, so if we are going to use the Bernoulli's equation, then we have to first choose our point 1, and here this will be our point 2. Okay, and now let's applying the Bernoulli's equation. All right. To solve for the velocity right here at this downstream end, to solve for v sub 2. Okay, so p sub 1 by divided by the the pressure head, plus z sub 1 plus the velocity head is just equal to the pressure head at point 2 plus the elevation head at point 2 plus the velocity head at point 2. Okay, so we notice that this is actually exposed to the atmosphere, to the atmospheric pressure, and therefore if we work on the gauge pressure, this will be 0, and then this one would also be 0. Again, they're 0 is because they are exposed to the atmospheric pressure, and we're talking about we're dealing with gauge pressure. In terms of gauge pressure, this will be 0. Okay, for the velocity, for the elevation head, we have the values in the elevation head, right, at point 1 and point 2. So no, we can't just neglect this. Now for the velocity head, it says here that velocity head can be neglected and ignoring, right here. So the surface velocity behind the spillway is very small. So this has a small velocity as compared to this one. So I guess when referring to discharge, this should be the velocity at this section. Okay, so this velocity head at point 1 would also be 0. All right, now z1, let's solve for v sub 2. So z sub 1 minus z sub 2 is just equal to v sub 2 squared all over 2. Therefore v sub 2 is just simply equal to 2 times delta z, right? So we have 2 times 24 minus 0. This should be 2g. Sorry, this should be 2g. Right, so we have 2g. 24 minus 0.04. 0.41. Okay, times the gravitational acceleration, but in English units, and that's going to be 32.2 feet per second squared. Okay, so if you do the math, what you get is 38.98 feet per second. Okay, so now we have the velocity, so we can solve for the discharge. Okay, so the discharge, this is just the same discharge at point 1 is just equal to the discharge at point 2 based on the continuity equation, and therefore Q is just simply equal to the area times the velocity. Okay, so I think this velocity would be the velocity at the downstream end, right? Because if we are referring to the velocity at the upstream, then that's going to be 0, right? So we have to use this velocity at the downstream end. Okay, so our area is just simply this rectangular area, which is 0.41 times 50. 0.41 times 50, that's in feet, so that's feet squared, times the velocity of 38.98 feet per second. Therefore, we'll have a 799 feet cubed per second. Okay, so just to do a recap on our procedure. Now, this type of problem is actually an open channel problem because there's an exposure. I mean, the fluid surface, there's this surface is exposed to the atmospheric pressure. Okay, so we first apply the Bernoulli's equation because it says here that we can ignore the friction losses, and it mentions the velocity head. Therefore, we apply the Bernoulli's equation, and we can solve for the velocity at point 2. And once we have the velocity at point 2, then we can solve for the discharge. That's the volumetric flow rate. Okay, so that's 799 feet cubed per second. All right, now let's move on to the conservation of energy. Okay. Conservation of energy. Okay. Basically, what it means or what it states is that the total energy in the system is constant, right? Total energy in the system is constant. And that means that the energy in must be equal to the energy out. So the energy that you put into the system must be the same as the energy that you put out, or that's lost from the system. Okay, but for now, we're actually, I mean, since we're dealing with fluids, then we have already learned about the Bernoulli's equation, and it was actually an expression of the conservation of energy, except that it has some limitations in the losses, and there's no addition. I mean, what if there's an additional input energy from the pump? So those the Bernoulli equation is not, or does not yet accommodate those aspects. Okay, so this conservation of energy can be expressed in terms of the Bernoulli's equation plus the let's say plus the limitations, right? So if you remember, the Bernoulli's equation is the velocity, the pressure head at point 1 as the elevation head at point 1 plus the velocity head at point 1, right? So this is our Bernoulli's equation. It's just equal to the pressure head at point 2 plus the elevation head plus the velocity head, right? Now let's try to let's say we have a fluid right here, a source of fluid, and we want to lift this this water up here at point 2, right? So let's say this is our point 2, this is our point 1. So we want to lift our water from point 1 to point 2. So how would you do that without the, that's the opposite direction of the gravitational force. Therefore, you would need a pump. So if you have a pump, then you can actually lift the water. Okay, so because of the addition of pump, then of course that would require additional energy, right? So let's say we have H sub A. So this will be plus, okay, energy in plus H sub A. So any devices that adds energy into the system, and by the way, this pump is actually a device that increases the pressure so that you can have a flow, or so that the flow is from higher pressure to lower pressure. So let's say this is H sub A. That's the let's write here, H sub A is the energy added to the fluid with a mechanical device. And one example, or one typical example, is the pump, right? Example, pump, or let's say blowers for airs, or compressors. Okay, now we have this energy. Let's say from point 1, we have the pressure head, the elevation head, the velocity head, plus the add-on energy. Now at point 2, the exit would be the pressure head, elevation head, and velocity head. But we'll also have, it is if we take into account there are also devices that that removes energy from the system. So if this is our system, there are also devices that removes energy from the system. And an example is a turbine. So for turbines, for example, we have this device, and let's say it has some impellers, right? Okay, so let's say it has some impellers, and right here, let's say this is our inlet, and then this is our outlet. Now if we draw the side view, so this is just an illustration. So if we have a pipe right here, inlet, and then this is the outlet, then of course, if you have a fluid motion going inside, now because of the fluid force, then of course this would rotate, right? So basically, a turbine is something like a conversion, or a device that converts the mechanical and let's say the energy from the fluids into rotating shaft, right? So that's going to be output. If you have a shaft right here, well, because of the fluid motion that causes rotation, then the result would be a rotating shaft. So that rotating shaft is actually something that removes energy from the system. Okay, so this one would be H sub R. Okay, so H sub R is the energy removed from the fluid by a mechanical device. For example, fluid motor or turbines. Okay, so therefore, since this is an energy loss, then this will be on the right hand side, so H sub R. Okay, so additionally, when transporting the fluid from point 1 to point 2, since the fluid is actually enclosed in this pipe, then of course there's going to be frictional losses as well. Okay, so that would be accounted by the term H sub L. Okay, so plus H sub L. So H sub L, that's the energy losses from the system due to pipe friction and due to valves and fittings. Okay, so we have these additional terms in the Bernoulli's equations. So because basically we can say that the conservation of energy is the Bernoulli equation plus the additional energy if there's any, like for example there's a pump in the system, then you have to include that energy addition. And we that this conservation of energy equation is also accounts the energy removal, like for example the turbines, and the energy losses due to the friction in the along the pipe length and the fittings. For our first problem, we have this problem taken from the textbook by Mott and Antener. The problem says water flows from a large reservoir at the rate of 1.2 cubic feet per second through a pipe system as shown in the figure. Calculate the total amount of energy lost from the system because of the valve, the elbows, and other other parts. Also solve for the velocity at point 2. Okay, so this is actually something like an addition to the original problem. So that's the solve for the velocity at point 2. All right. Now this is our system. So we have a large reservoir here, and it is elevated. This is the let's say this is our point 1, and then this is our point 2. Because it says here that we have to solve for the energy loss. That's the H sub L. So the energy loss would just be due to the friction along the pipe wall. Okay, there's no pump, there's no turbines, and therefore the only term that's left is the losses due to pipe frictions. All right, so the first step to do is solution. So the first step to do is to establish the equation. Okay, so that's going to be our Bernoulli's equation plus the elevation head plus the velocity head, right? Plus for our pump, for example, our HA. Okay. And then this one at point 2. Okay, plus the remove plus H sub L. Okay, so for our pressure head, that's established, by the way, our point 1. So this will be our point 1, and then this will be our point 2. Okay, so for the velocity head, so our pressure head, this is actually 0, because if you recall in our previous discussions regarding the large reservoir, the velocity here with respect to the velocity at this smaller area, then this velocity is negligible. Okay, so the pressure head is 0, the elevation is not, the velocity head, this is also 0. Again, that's from our previous discussion. Then there's no pump, there's no addition of energy, so this term would be 0. Now in for point 2, section 2, since this is our point 2, okay, that's outside, and if it's outside, then that's gonna be exposed to the atmospheric pressure, and therefore this one would be 0. Then this one that depends upon the reference point. The velocity right here, since we are given by this dimension, it says here 3-inch diameter, then if we apply the continuity equation that Q is equal to AV, if we apply the flow rate equation, Q is equal to AV, then we can solve for this V sub squared. And for our H sub R, we don't have this, and this one is present, and therefore The only unknown is the velocity, right? The velocity and this HL. But the velocity, you can solve that using this, using the flow rate equation. So therefore, the equation would just be Z1 minus Z sub 2, right, minus the velocity head at point 2 is equal to the head loss. Okay, now let's solve for V sub 2 using the flow rate equation. Okay, so V sub 2 is equal to Q all over area. Okay, our Q is that's given, right, 1.2. So this is 1.2 feet cube per second divided by our area, which is pi, times times 3 inch. Of course, you have to convert that into feet. So 1 foot is equal to 12 inches. This is squared all over 4, and therefore what you get is 24.45 feet per second. Okay, now since you have the velocity, then you can now solve for the head loss, the HL. So HL is just equal to Z1 minus Z2. So this is our reference point, then that delta Z is just simply 25, right? That's 25. So that's 25, right, minus the velocity head, 24.425. That's squared divided by 2 times the gravitational acceleration, which is 32.2 feet per second squared. Alright, so we have 25, and this term right here is equal to 9.28 something. And of course, this is in feet and this is in feet. Therefore, this is equal to 15.72 feet. Okay, so again, in this problem, we don't have mechanical devices that adds energy. We don't also have mechanical devices that removes energy in the system, and therefore the only term that's left in our conservation of energy equation is the head loss. Okay, so if we substitute all the values, and by the way, we obtain the velocity by using the flow rate equation, and once you have that, then you can solve for the head loss. Okay, so in the next video we will be doing another problem regarding this conservation of energy, and then we'll move on to the conservation of momentum. See you in the next video.